Welcome to Talk Tensors.
Glad to be here for this one.
So let's cast our minds back to 2015.
A very different era.
Right. I mean, if you were an engineer back then, trying to build, say, an autonomous vehicle, and you needed an algorithm to accurately draw a box around a pedestrian in a live video feed, you had to accept a pretty harsh reality.
You really did.
Your highly accurate state-of-the-art system was going to process that video at a sluggish 7 frames per second.
Yeah. 7 frames.
Which is wild to think about now.
Yeah.
At highway speeds, by the time your system finished rendering the bounding box on frame 1, the car had already traveled like 50 feet.
Exactly. And the entire computer vision industry was sort of paralyzed by this core assumption. It was this idea that you could have real-time speed or you could have high mean average precision, but you absolutely could not have both.
Right, because the underlying geometry of neural networks at the time dictated that it was a trade-off.
It was treated as an immutable law of physics within the field. I mean, you had the RCNN family of detectors, specifically faster RCNN, and they were just dominating the accuracy benchmarks.
They were heavy.
So heavy. Their architecture inherently relied on a computationally punishing 2-stage pipeline. The network essentially had to pause, hypothesize thousands of potential object regions, physically crop and resample the feature maps for every single one of those regions, and then run them through a second classifier.
Which takes forever in compute time.
Right. That resampling bottleneck is exactly why you maxed out at 7 frames per second.
And if you couldn't afford that bottleneck, if you needed the speed, you defected to the other camp. You used YOLO.
You only look once.
Exactly. YOLO forced the entire image through a single grid in one pass. And it hit an astonishing 45 frames per second, which, finally made real-time video processing viable.
Yeah, the cost was severe.
Huge. On the standard Pascal VOC 2007 dataset, faster RCNN achieved a 73.2% mean average precision. But YOLO dropped all the way down to 63.4%. Yeah. I mean, in the context of computer vision benchmarks, sacrificing 10% of your precision to gain speed, that isn't just a compromise, it's a completely different use case.
Which is exactly why the paper we are dissecting today was such a structural earthquake when it was published in 2016.
Oh, absolutely.
We're doing a deep dive into SSD single-shot multi-box detector by Wei Liu and a team of researchers from UNC, Zoox, Google, and Michigan.
And the mission of this deep dive is to really unpack how they pulled this off.
Yeah.
Because they didn't just optimize the existing pipelines, right?
No, they didn't. They formulated a mathematical thesis proving that by discretizing the output space of bounding boxes into varied aspect ratios, and this is the key part, distributing those boxes across multiple feature map layers of declining resolution, a single unified neural network could completely eliminate the 2-stage bottleneck.
They bypassed the region proposal step entirely.
Entirely.
And the metrics speak for themselves.
Yeah.
SSD achieved 59 frames per second, which is significantly faster than YOLO, while simultaneously hitting 74.3% accuracy.
Meaning it outperformed the heavy, slow, faster RCNN.
Which is having your cake and eating it too.
Yeah.
So for you listening, we need to look at exactly how they engineered their way out of that trade-off. And we should probably start with the base architecture.
Good place to start.
Because if you're going to completely remove the second stage of a detector, your initial feature extraction has to be incredibly robust.
It has to do a lot of heavy lifting.
Right. So they started with the standard VGG16 architecture, which was pre-trained on ImageNet. But they had to perform some highly specific surgery on it before adding their detection layers.
Yeah, taking a classification network like VGG16 and forcing it to perform spatial detection requires some fundamental structural changes. Because think about it, a classification network is inherently designed to destroy spatial information.
Right, it doesn't care where the dog is, just that there is a dog.
Exactly. It takes a 300 by 300 pixel image and funnels it down into a single one-dimensional vector of class probabilities. So to prevent that spatial destruction, the authors had to sever the network before those final fully connected layers.
They just chop them off.
Well, they took the fully connected layers, FC6 and FC7, and converted them into standard convolutional layers.
Okay, which is a relatively standard move for detection networks.
Yeah.
But it's what they did to the pooling layers that altered the receptive field, right?
Yes. They changed the pool 5 layer from a 2x2 grid with a stride of 2 down to a 3x3 grid with a stride of 1.
Wait, let me make sure I have this. When you change the stride of a pooling layer from 2 to 1, you stop having the spatial dimensions of your feature map.
Correct. You preserve resolution, which is critical for finding objects, but you immediately introduce a massive problem for the subsequent convolutional layers.
Because their filters are now looking at a comparatively smaller patch of the original image.
Exactly. You've shrunk their receptive field.
Ah. And if the network can't see as widely across the image, it loses the global context required to detect large objects.
Precisely. The authors resolved this by implementing the Etruce algorithm.
Which is more commonly referred to today as dilated convolutions, right?
So instead of adding padding or changing the stride again, they physically spaced out the weights inside the convolutional filters in those converted layers. They injected holes into the kernel.
Okay, so a standard 3x3 kernel looks at 9 adjacent pixels in a tight little square. A dilated 3x3 kernel with a dilation rate of 2 still only uses 9 parameters, but it spreads them out.
Exactly. It skips a pixel between every weight.
So it covers a 5x5 area of the feature map without increasing the computational load of the filter itself.
It's so elegant. It allows the network to maintain a massive field of view without aggressively downsampling the spatial resolution.
That's brilliant.
And once they secured this modified, fully convolutional VGG16 base, they had a really strong feature extractor. But, and this is crucial, if they stopped there and just predicted bounding boxes from that final layer, they would run into the exact same limitations as YOLO or overfeed.
Because predicting everything from a single high-level feature map severely limits your ability to detect objects of vastly different scales.
Right, and this is where we hit the core architectural divergence of SSD, the secret sauce, if you will.
The multi-scale feature maps.
Yes, they didn't stop at the VGG base. They appended a cascading series of extra convolutional feature layers to the very end of the network.
And these layers progressively decrease in spatial size.
Yep. For a standard 300 by 300 input image, the network generates a feature map that is 38 by 38 cells. Then deeper into the network, it generates a 19 by 19 map, then a 10 by 10, a 5 by 5, a 3 by 3, and finally a tiny 1 by 1 map.
So the physical intuition here is really important. Think about the mechanical degradation of spatial data as it flows through these layers.
Right, as you go deeper.
The 38 by 38 feature map still retains a relatively granular mapping of the original input pixels. It possesses the high-frequency spatial detail you'd need to localize tiny objects.
But as you apply more convolutions and flow down to the 5 by 5 or the 1 by 1 map, you are heavily compressing the data.
You are trading spatial resolution for deep, abstract semantic understanding.
Exactly. A single cell in that 1 by 1 map might represent an aggregation of features spanning the entire original image.
It's the difference between looking at a landscape through a telephoto lens versus a wide-angle lens.
I like that analogy.
Like if you are standing on a balcony trying to find a pigeon on the sidewalk, you need the telephoto lens. The pigeon only occupies a tiny fraction of your field of view, so you need intense, localized detail.
That is your 38 by 38 feature map.
Right. But if a massive, articulated city bus drives past, the telephoto lens is useless. You'd only see a blurry patch of yellow metal. You have to swap to the wide-angle lens to capture the entire geometric boundary of the bus.
And that is your 1 by 1 or 3 by 3 feature map. And what makes SSD special is that it doesn't force you to choose lenses. It actively makes predictions from all of these cascading layers simultaneously.
Wow. And that simultaneous prediction is handled by what they call convolutional predictors.
Yes. Because the network is fully convolutional, there are no dense layers wiping out the spatial grid. So for any given feature layer, let's say a layer that is M cells wide, N cells high, with P channels, SSD applies a very small 3 by 3 by P convolutional kernel.
And this kernel slides across every single discrete location on that M by N grid.
At every stop along that grid, that tiny kernel computes two distinct outputs. First, it computes a set of confidence scores for every possible object category.
So if you were training on a data set with 20 classes, it outputs 20 probability scores plus 1 extra score for the background class.
Exactly. And second, and this is where the geometry gets intricate, it computes a set of 4 shape offsets.
But it's not predicting the absolute X and Y pixel coordinates of the object, is it?
No, it predicts offsets relative to a predefined default box.
We definitely need to examine these default boxes carefully because they seem to be the mechanism that allows the network to discretize the infinite, continuous space of an image into a finite, predictable math problem.
That's exactly what they do. At every single cell in that feature map grid, the network projects a fixed set of default boxes onto the image.
Okay.
The network evaluates the image and essentially says, I am highly confident there is a vehicle located in this specific grid cell. However, the vehicle doesn't perfectly match the dimensions of my default square box.
So to make it fit, you need to shift the center point of the box a few pixels to the right, increase the width by 10%, and decrease the height by 5%.
You've got it. It learns to regress the adjustments, the delta between the fixed default box and the ground truth object.
But objects don't just vary in scale, right? They vary wildly in their aspect ratios.
Oh, massively.
I mean, a pedestrian standing upright is a tall, narrow rectangle. A license plate is a short, wide rectangle. If you only provide the network with square default boxes, it has to work incredibly hard to regress the offsets for that standing pedestrian.
The gradients would be massive. It would be highly inefficient.
So how do they fix that?
To prevent that, the authors associated a specific variety of aspect ratios with the default boxes at each grid location. They mathematically enforced ratios of 1, 2, 3, 12, and 13.
Okay, meaning at any given point, the network starts with a baseline square, a rectangle twice as tall as it is wide, a rectangle 3 times as tall, and the horizontal inversions of those shapes.
Exactly. And we have to combine those aspect ratios with the multi-scale feature maps we discussed earlier.
Right, the telephoto and wide-angle lenses.
The paper outlines a specific linear step function to distribute the scale of these boxes across the different layers. Instead of reading the raw algebra, let's just look at the behavior of the math. They set the scale of the boxes on the lowest, most detailed layer to 20% of the original image size. Then, they set the scale for the highest, most abstract layer to 90% of the image size.
And for all the intermediate layers.
The scale just steps up evenly and predictably between those two bounds.
So on the 38 by 38 map, your default boxes are clustered around that 20% scale. They are small.
Yes. And on the 5 by 5 map, your default boxes are massive, covering 70 or 80% of the image.
When you cross-multiply the varied aspect ratios with these progressive scales, you give the network a highly tailored geometric template for almost any object in the real world.
It's incredibly thorough.
Let's actually map this to the visual dataset examples provided in the research just to ground it. Consider an image of a complex street scene.
Okay, I'm picturing it.
In the background, there is a pedestrian holding a clear umbrella walking away from the camera. Because they are distant, they occupy a tiny sliver of pixels.
Right. So the 5 by 5 feature map deep in the network with its massive 80% scale boxes will completely ignore that pedestrian. The convolutional filters on that layer are mathematically blind to features that small.
However, on the very early 38 by 38 feature map, the network deploys a default box with a 20% scale and a 13 aspect ratio, a tall, very narrow rectangle.
And that specific default box aligns perfectly with the geometry of the distant pedestrian.
Yes. Conversely, look at the other visual example we have. A city bus driving through the foreground with a bicycle mounted on the front rack.
The 38 by 38 layer is useless for detecting the bus as a single entity. Its boxes are far too small. It might identify a tire or a window, but not the bus itself.
But the 3 by 3 feature map, utilizing a wide aspect ratio default box at a 90% scale, perfectly encapsulates the entire boundary of the bus.
The network inherently learns which layer acts as the appropriate filter for specific scales.
It's beautiful, but this elegant division of labor creates an immediate, staggering data problem.
Oh, absolutely. The combinatorics get out of hand quickly.
If we calculate the total number of predictions, taking the number of classes, plus the 4 shape offsets, multiplied by the number of default boxes per location, multiplied by the total dimensions of all the feature maps combined, we get a massive number.
For a standard 300 by 300 image, SSD generates exactly 8,732 default boxes per single frame.
8,732 localized predictions evaluated simultaneously.
It's a lot.
Which introduces a brutal training bottleneck. How do you calculate the loss function for 8,732 overlapping boxes?
Right, because during training, you have your human annotated ground truth box, say a single box drawn around a dog. You have to assign that single ground truth to your pool of 8,732 guesses, so the network knows which parameters to update.
And this is known as the bipartite matching problem.
Exactly. Now, previous architectures typically solved this by finding the single default box that had the absolute highest Jacquard overlap with the ground truth box.
The Jacquard overlap, or intersection over union, just measures the area where the two boxes overlap divided by the total area they both cover, right?
Correct. And if you only match the ground truth to the single best box, you ensure that only the most accurate spatial filter gets updated. SSD starts with this step. It finds the absolute best match, but then it does something highly counterintuitive.
What does it do?
It goes back through the remaining 8,731 boxes and matches the ground truth to any default box that has a Jacquard overlap higher than 0.5.
Okay, I really want to push back on the logic of that choice, because geometrically that seems like a recipe for destabilization.
It does sound like it initially.
If I have a perfectly drawn ground truth box around a dog, and I associate it with the best default box, the network learns the exact boundaries. But if I lower the threshold to 0.5, I am now telling the network to strongly associate the dog label with a box that might be shifted heavily to the left, or a box that is far too wide, simply because half of it overlaps with the dog.
You're blurring the target.
Exactly. Aren't we deliberately blurring the target? Aren't we training the network to be sloppy with its localization?
That is the natural intuition, but if you look at the gradient behavior during backpropagation, strict sparsity is actually your enemy here.
Really? How so?
Think about it. If you only pick the single best box, your positive training signals are incredibly sparse. You have 8,731 negative signals and exactly one positive signal.
Oh.
The network gets punished for predicting a bounding box that is 80% accurate simply because another box was 81% accurate.
Yeah.
The loss landscape becomes incredibly sharp and difficult to traverse.
That makes sense.
By lowering the threshold to 0.5, you flood the network with positive signals. You allow the network to confidently predict high scores for multiple overlapping default boxes that capture the general spatial domain of the object.
So you are sacrificing micro-precision during the forward pass to guarantee macro stability during gradient descent.
Precisely. You rely on the post-processing step, specifically non-maximum suppression, to act as the janitor and clean up the highly overlapping duplicate boxes during inference.
Fascinating. So once you have those positive matches established, you have to penalize the network for its mistakes.
Right, the loss function. The loss function SSD employs is a weighted sum of two distinct error calculations: the confidence loss and the localization loss.
Let's break those down. The confidence loss is a standard softmax loss applied over all the multiple class confidences.
Yeah, it handles the semantic error. If the network looks at a motorcycle and outputs a high probability for a bicycle, the softmax loss penalizes that misclassification.
It also heavily penalizes the network if it predicts an object where there is only background, right?
Yes, exactly. And then the localization loss handles the geometric error. It measures the delta between the predicted shape offsets the center X, center Y width, and height in the actual ground truth dimensions.
But the specific function they use is critical. They use a smooth L1 loss rather than a standard L2 squared error loss.
And the difference in the derivative curves there is vital.
Because an L2 loss squares the error. If a default box is slightly off, the penalty is small. But if a default box is wildly off, which happens constantly in the first few epochs of training when the weights are essentially random squaring, a massive error creates a massive number.
And that massive number translates into an exploding gradient during backpropagation. The weight updates become so large that the network's parameters oscillate wildly and the model fails to converge.
It just breaks.
Pretty much. Smooth L1 behaves like an L2 loss for very small errors, allowing for fine-tuning, but it transitions into a linear L1 loss for large errors. It physically caps the gradient, acting as a mathematical shock absorber during early training.
It keeps the training stable. But even with smooth L1, the loss function is about to hit a brick wall, which we can call the imbalance crisis.
Uh-oh.
Let's return to our 8,732 default boxes. If we're looking at an image of a dog in a park, maybe 30 of those default boxes achieve that 0.5 Jacquard overlap with the dog. That leaves exactly 8,702 default boxes that are matched to absolutely nothing. They're empty background.
And this imbalance mathematically breaks the softmax confidence loss.
Because if you feed all 8,732 examples into the loss function, the gradients generated by the 8,702 background boxes will completely drown out the gradients generated by the 30 dog boxes.
The neural network will optimize for the path of least resistance. It will realize that it can achieve 99.6% accuracy simply by predicting background for every single box every single time.
It will entirely lose the ability to detect objects.
To fix this, the authors implemented a brutal data filtering technique called hard negative mining.
Brutal how?
Well, they don't randomly sample the background boxes. Instead, after the forward pass, they take all 8,702 negative background examples and sort them based on their confidence loss. They isolate the background boxes where the network made the most egregious mathematical errors.
These are the false positives. The network looked at a shadowy fire hydrant and was highly confident it was a dog. Or it looked at a rectangular reflection in a window and was highly confident it was a car.
Exactly. The confidence loss on these specific background boxes is massive. The authors take these top offending hard negatives and they completely discard the thousands of easy negatives, the blank sky, the flat asphalt, where the networks correctly guess background with high confidence.
And they don't just use all the hard negatives either. They enforce a strict non-negotiable ratio. For every one positive object box, they are only allowed to keep 3 hard negative background boxes, a 3-to-1 ratio.
And I think it's worth questioning the rigidity of that 3-to-1 ratio. Why not 1-to-1 to perfectly balance the data set? Or why not 10-to-1 to ensure the network is exposed to a wider variety of background textures?
Well, if you go 1-to-1, you risk catastrophic forgetting of what a standard background actually looks like. The network becomes so hyper-focused on objects that it starts hallucinating them in empty space.
Makes sense. And if you go 10-to-1,
then you start reintroducing the imbalance crisis. The gradients from the boundary case backgrounds begin to overwhelm the object gradients again. So 3-to-1 is the empirical sweet spot.
it forces the network to spend its computational energy entirely on the boundary cases, distinguishing the actual geometric boundaries of objects from the chaotic textures of the real world without letting the background dominate the loss function.
And the authors state, this specific ratio is what allows the optimization to converge faster and remain stable.
It solves the background problem, sure, but it doesn't solve the architecture's inherent geometric weakness.
Which Talk Tensors always has to highlight. What did they get wrong? What do they struggle with?
If we look at the diagnostic error plots provided in the paper, the authors are completely transparent about SSD's primary failing. The architecture is highly sensitive to bounding box size. Specifically, its performance on extra small objects is significantly worse than two-stage detectors like faster RCNN.
Which is the direct, unavoidable consequence of eliminating the region proposal network.
Exactly. In faster RCNN, if the first stage detects a cluster of pixels that might be a tiny object, it uses region of interest pooling.
ROI pooling.
Right. It physically crops that tiny patch of the feature map, resamples it, and interpolates it back up to a fixed size. It effectively acts as a digital zoom, forcing the classifier to look at those specific pixels again with full computational attention.
But SSD physically cannot do this.
Yeah.
Once the image enters the VGG16 base, the data just continuously flows forward, degrading in spatial resolution at every pooling layer.
By the time the image data propagates up to the highest layers, a tiny object in the original image might not even activate a single discrete neuron. The spatial footprint is entirely lost.
Without that secondary resampling step, the network simply locks the high-frequency detail required to classify it.
So you have a rigid architecture that inherently struggles with small objects. And you can't introduce resampling without destroying your 59 FPS speed advantage.
So how do you solve a structural limitation without changing the structure?
You change the data.
You change the data. The authors leveraged extreme data augmentation to mathematically force the network to learn robust representations of small objects. They utilized a technique we can call the zoom-in, zoom-out fix.
Now, standard data augmentation is a given in these pipelines, horizontal flipping with a 0.5 probability, applying photometric distortions to alter the brightness, contrast, and saturation.
Right. SSD applies these just to prevent the network from memorizing the specific color profiles of the training set.
They also utilize random patch sampling, cropping out sections of the image. This acts as the zoom-in operation. If you take a medium-sized object and crop tightly around it, you feed the network a training example where the object appears massive relative to the frame.
But the real ingenuity was how they engineered the zoom-out operation to fix the small object deficit. They created the expansion trick.
The expansion trick.
They recognized that they didn't have enough varied examples of microscopic objects in the dataset to properly train those 38 by 38 feature maps. So they synthetically generated them. They take the original standard-sized training image, and they drop it onto a massive blank digital canvas.
Specifically, a canvas that is 16 times the original image size. And they fill the empty space of this canvas with the mean pixel values of the entire data set.
And that specific detail, filling it with the mean pixel values rather than just black or white pixels is highly critical.
Why is that?
Because if you fill a 16x canvas with pure black, you create an incredibly sharp artificial edge where the real image meets the black void. The convolutional filters will instantly lock onto that artificial edge, treating it as the most prominent geometric feature in the image, completely ignoring the objects inside.
Oh, wow. So by filling it with the mean pixel values, you create a neutral, mathematically invisible boundary.
Precisely. Once the original image is sitting in the middle of this massive neutral canvas, they take their random crops. If you crop a 300 by 300 section from that expanded canvas, and the original image happens to be caught in that crop, the objects inside that image are now completely dwarfed by the surrounding space.
A normal-sized car is suddenly rendered as a tiny speck of pixels in a massive void.
They artificially engineered thousands of perfect training examples for microscopic objects without needing to physically collect a single new photograph.
That is incredibly clever, and the ablation metrics prove how vital this was. When they introduced the expansion trick, they saw a massive 2 to 3% increase in mean average precision across the data sets.
For a mature architecture, a 3% jump strictly from a data augmentation pipeline is staggering.
It proves that for a single-shot detector without region of interest pooling, synthetic data expansion isn't just a nice regularization technique, it is a load-bearing pillar of the architecture.
Absolutely. So with the architecture unified, the loss function stabilized through hard negative mining, and the spatial deficit mitigated through expansion, we have to look at whether these aggressive, somewhat brute force solutions actually translated to generalized accuracy.
Did they overfit the model to specific shapes, or did it truly rival the two-stage networks?
Well, the results on the Pascal VOC 2007 test set are what cemented this paper's legacy. Utilizing a relatively small input image size of 300 by 300 pixels, SSD 300 hit 74.3% mean average precision while processing 59 frames per second.
It surpassed the accuracy of faster RCNN while operating nearly 8 times faster.
And they scaled it up by simply increasing the input resolution to 512 by 512 pixels, which physically provides the network with more high-frequency spatial data to detect small objects. SSD 512 hit 76.9% MEP.
The frame rate dropped to 22 FPS due to the increased computational load of the larger feature maps, but 22 FPS is still fast enough for many continuous video applications.
And it absolutely crushed faster RCNN's 73.2%. They validated this robustness on the KioCO dataset as well, which is a notoriously difficult benchmark due to its high density of small occluded objects.
Right, coupling M is brutal.
SSD 512 consistently beat faster RCNN across the strict intersection over union metrics there too.
But top-line metrics only tell you that a system works. They don't prove why it works. To understand the mechanics, we have to look at their ablation studies.
My favorite part. This is where you systematically delete components of the architecture and measure the resulting degradation. If we remove a piece and the accuracy doesn't drop, that piece was mathematically useless.
So what happens to the network if we remove the varied aspect ratios we discussed earlier?
The paper proves that the geometric diversity of the default boxes is absolutely non-negotiable. If you strip away the 13 and 3 aspect ratio boxes, removing the network's ability to initialize tall, skinny boxes and short, wide boxes, the overall performance drops by 0.6%.
And if you push it further and delete the 12 and 2 aspect ratios, forcing the network to rely almost entirely on square default boxes,
the performance plummets by an additional 2.1%.
Wow. It physically cannot regress the spatial offsets for irregular objects fast enough without those targeted starting templates.
It needs them. And what about the multi-scale feature layers? We spent a lot of time discussing the progressive downsampling from 38 by 38 down to 1 by 1. What if we force SSD to behave like older single-shot architectures and only predict from a single deep layer?
They tested this by forcing the network to generate all its predictions solely from the Conv v7 layer. The degradation was catastrophic.
How bad?
Overall accuracy plummeted from 74.3% down to 62.4%.
Yikes.
Yeah, losing 12% of your precision completely breaks the viability of the model. This specific ablation isolates the exact mechanism of their success. Spreading the default boxes across layers with progressively expanding receptive fields is the absolute beating heart of the SSD architecture.
However, the error analysis tool utilized by the authors did expose a specific persistent friction point. Because SSD directly regresses the shape offsets in a continuous forward pass, its localization error, its ability to draw tight bounding boxes, is actually lower than the two-stage methods.
Right, it's good at drawing the box.
But it suffers from a higher rate of categorical confusion between similar objects.
Yes, the confusion matrix clearly shows SSD struggling to differentiate between specific classes of animals. It will frequently output a high confidence score for a dog when the object is actually a cat, or mislabel a sheep as a cow.
And the authors postulate this is a direct side effect of the multi-scale architecture. Because multiple object categories are forced to share the exact same locational filters and default box geometries on a given feature map, the semantic boundaries blur.
Think back to the visual dataset examples. We have an image of a heavy cow grazing in a glassy pasture, and we have another image of a horse jumping over a wooden fence in a field.
Right.
If you look at those two images from the perspective of a highly compressed 5x5 feature map deep in the neural network, the high-frequency textural details, the hair, the shape of the snout are entirely gone.
The geometric profile of a cow in a field and a horse in a field are mathematically almost identical at that resolution.
They are both large, horizontally oriented quadrupedal blobs situated in a green spatial context.
Because SSD relies so heavily on matching the geometric profile of the default box on those deep layers, and it doesn't have a second stage classifier to resample the pixels and look for a mane or horns, it mislabels the specific class because the low resolution geometries are too similar.
Which, in the grand scheme of deployment, is a remarkably minor trade-off to achieve 59 frames per second.
Oh, absolutely. The legacy of this paper is defined by how it fundamentally altered the trajectory of applied machine learning. Prior to SSD, single-shot detectors were viewed as a compromised gimmick.
You use them for real-time applications where you explicitly didn't care about rigorous accuracy. SSD eradicated the assumption that you needed a two-stage pipeline to win state-of-the-art benchmarks.
It proved that the pipeline could be collapsed. And the core mathematical insights of this paper, specifically the implementation of multi-scale feature maps and the geometric tiling of anchor boxes, became the foundational building blocks for almost all edge device computer vision that followed.
For years, if you were building a drone that needed to navigate a forest or a mobile phone app that needed to track a face in real time, your system was likely utilizing descendants of the architecture. Wei Liu and his team pioneered here.
The authors even explicitly noted in their conclusion that because SSD is a monolithic feed-forward matrix multiplication, it provides a mathematically stable foundation for integration with recurrent neural networks to track temporal movement in video feeds simultaneously.
It is an architecture built for continuous data streams.
Which perfectly transitions us into my favorite part of the deep dive, the novel notions segment.
I must provide the necessary rigorous disclaimer.
Proceed.
The following segment is highly speculative. We are taking the verified mechanics of the paper and extrapolating them into unproven theoretical domains. This is intended strictly for entertainment purposes and pushing the boundaries of the established concepts.
Thank you. So we are taking the core philosophies of SSD and turning them up to 11. Idea number 1, differentiable, context-aware tiling via reinforcement learning.
Okay, I'm listening.
Here's the premise. In the original architecture, the mathematics of the default boxes, the linear step function from a scale of 0.2 to 0.9, the rigid aspect ratios of 1, 2, and 3 are entirely hard-coded hyperparameters.
Right. The authors empirically designed them by hand based on human intuition about typical object geometries in standard datasets.
But what if we forced the network to dynamically learn its own optimal tiling geometry on a per-image basis?
You're proposing a dynamic pre-computation step. How exactly would the architectural mechanism execute that?
We train a lightweight, highly optimized reinforcement learning agent. This RL agent acts as a gating preprocessor. As the image passes through the VGG6 tune base, the RL agent taps into the very first high-resolution feature maps.
Before any of the multi-scale detection layers fire.
Exactly. The RL agent analyzes the spatial context of the image. It recognizes the semantic environment. It says, okay, the feature distribution indicates this is a macro photograph of a slice of pizza, or the feature distribution indicates this is a wide aerial landscape shot of elephants in a savanna.
And then what?
Based entirely on that recognized context, the RL agent dynamically outputs a bespoke set of scales and aspect ratios perfectly tailored to that specific scene. It literally alters the physical geometry of the default boxes on the fly before the convolutional predictors ever evaluate them.
That's wild. The probability mapping for this concept presents two distinct scenarios. Scenario A, high probability, moderate impact. The mathematics of the RL agent function correctly. The agent successfully morphs the default boxes to match complex scenes, and the mean average precision increases on highly irregular objects. However, the computational friction of running an active policy network on every single frame completely destroys the feed-forward simplicity of SSD. You lose the 59 FPS advantage. It becomes completely non-viable for autonomous cars or real-time drones.
But it could become a paradigm-shifting tool in domains where processing speed is entirely secondary to absolute pixel-perfect precision-like medical imaging.
Oh, that's true. If the RL agent can dynamically alter its default boxes to match the precise, highly irregular scales and non-linear boundaries of microscopic tumors on an MRI scan, that is a massive clinical breakthrough.
And then there is scenario B, low probability, high impact.
The fun one.
The RL agent is unleashed on a dataset of millions of natural images, and it discovers a universal mathematical grammar of aspect ratios that human engineers simply haven't conceived of.
It completely abandons the rigid 1, 2, and 3 ratios and instead generates nonlinear, mathematically bizarre geometric shapes and scaling progressions that map perfectly to the fractal nature of the real world.
It proves that human intuition regarding spatial geometry was actually the bottleneck holding the architecture back all along.
Analyzing the geometric outputs of that RL agent would be a fascinating paper in itself. Let's move to idea 2. Spatiotemporal default tubes for video streaming.
I love this one.
The original SSD authors briefly hinted at video tracking applications. I propose we take their 2D default box tiling and expand it into 3D default tubes that physically stretch across the temporal dimension, explicitly representing time.
I love the mechanics of this. How do we alter the convolutional predictors to handle a tube?
Well, in standard SSD, the small convolutional filters predict 4 shape offsets: center X, center Y, width, and height. We expand the filters into 3D convolutions. They now predict 6 distinct offsets: center X, center Y, width, height, time start, and time duration.
So instead of feeding the network a single static image, you feed it a volumetric batch of 30 sequential video frames simultaneously.
Yes, the network executes a single forward pass and outputs a 3D mathematical tube that encapsulates an object's entire trajectory over those 30 frames.
Let's map that to a visual example. Imagine feeding the network 30 frames of a skateboarder executing a kickflip over a wall, or 2 kids aggressively swinging field hockey sticks at a ball.
Right, highly dynamic motion.
Instead of running the SSD architecture 30 separate times, generating 30 individual bounding boxes, and then relying on a computationally heavy recurrent neural network or a Kalman filter to stitch those boxes together over time, the 3D default tube captures the entire physical motion, the arc of the jump, the swing of the stick in one unified, continuous mathematical representation.
The critical friction point in proving this would be the loss function. You would take a heavily annotated, high frame rate data set of moving vehicles and complex traffic. You apply the 3D convolutional kernels to the modified base network.
And the key to making this converge is forcing the smooth L1 localization loss to account for a 5th dimension, velocity or temporal drift.
Exactly. You have to aggressively penalize the network if the predicted 3D tube bends or accelerates at a physical angle that a car cannot realistically achieve due to momentum.
You are effectively forcing the single shot detector to implicitly learn the laws of physics and momentum directly through the geometry of its loss function.
If you can achieve that stable convergence in a single forward pass, you entirely bypass the need for separate tracking algorithms. It is taking the exact philosophical premise of the SSD paper, eliminating the middleman by unifying disparate pipeline stages and projecting it into the dimension of time.
It is a logical extrapolation of mathematically collapsing the pipeline.
Absolutely.
And that philosophy is the perfect way to encapsulate this paper. Wei Liu and his team looked at a computer vision ecosystem that was entirely bogged down by the assumption that region proposals and classifiers had to exist in separate sequential stages. They engineered a mathematical unification.
By removing the resampling bottleneck, leveraging the progressive abstraction of multi-scale feature maps, and utilizing highly tailored tiling geometry, they shattered the speed accuracy trade-off.
It reinforces the reality that the most profound leaps in machine learning performance rarely come from simply throwing more computing power at an inefficient pipeline. They come from radically redefining how the network physically perceives the geometry of the data.
Exactly. We encourage you to look critically at your own machine learning architectures and data pipelines. What accepted 2-stage processes are you currently relying on that might just be an artifact of an old assumption?
What messy handoffs in your code could be collapsed into a single, elegant forward pass through clever data augmentation or geometric tiling?
Thank you for analyzing this architecture with us.
This has been Talk Tensors. And remember, the next time you find yourself stuck between choosing speed or choosing precision, sometimes the fastest way to read the document isn't to skim it, it's to build a better lens.